folks, I'm Doug Jones from Danley Sound Labs. This video is part of our series covering the basics. In this video, I'm going to explain the decibel. The decibel has its roots back in the early days of telegraph and telephones. Remember when your telephone was connected to every other telephone by wires? Well, back then, engineers needed to know how much power loss there was between various devices, because at the beginning, power was a precious commodity. Amplifiers were costly and inefficient, and so conserving every watt of power was critical. Accounting for the loss in telephone cable was a big deal. For example, how much power do you lose through a mile of wire? Well, they realized that measuring the power in watts at one end and then measuring the power at the other end was cumbersome. The actual number of watts was not the issue. They needed a way to quantify the loss in the cable. Not surprisingly, the first attempt at quantifying the loss was called the MSC, or Miles of Standard Cable. In the 1920s, it was proposed that the unit be called the bell, in honor of Alexander Graham Bell, with the working unit being 1/10 of a bell, or the decibel. So let's see how this works. The decibel is calculated in the following way. The decibel is equal to 10 times the log base 10 of the ratio of two powers. So let's say that we apply 10 watts to one end of a telephone line, and at the other end we measure 5 watts. Well, if we do the math, we see that we get a -3, or a 3 dB loss. That 3 dB loss would be there no matter what we start with. If we put 100 watts in, we'd get 50 watts out, a 3 dB loss. If we put 842 watts in, we would get 421 watts out, again, a 3 dB loss. What's cool is, if you flip the numbers, and you put 20 watts into something and for some reason 40 watts came out, you would also have 3 dB, but we'd call that gain. Pretty nifty. So now, the various segments of cable or networks could all be described by their loss or gain in decibels. So we see that the decibel has at least two features that make it attractive. It deals with ratios, so it's perfect for things like gain and loss, and even things like a signal-to-noise ratio. The other thing that might not be so obvious is that the decibel handles really large numbers very well. A change of 1 million watts to 2 million watts is still a 3 dB change. But there's a third feature that makes the decibel even more valuable to us in audio, and that is the very logarithmic nature of the dB. I'm fascinated by the fact that the way we have chosen to quantify and measure our universe is not often the way that we experience the universe. Our senses do not follow the nice linear progressions that most of our measurement systems do. For example, if you light one candle, it produces a certain amount of light. But 2 candles don't seem to be twice as bright as 1. In fact, doubling the amount of candles does not make it twice as bright, no matter how many candles you start with. The same is true in the perception of sound. 2 equal sound sources combined together do not create sound twice as loud as 1. As it turns out, our senses are much closer to being logarithmic than they are linear, and the decibel system is well suited for describing changes in ways that just feel right to our senses. Now, one of the drawbacks to the decibel, I suppose, is that in its basic form, it cannot be used to describe absolute values. We know that a certain amount of telephone wire creates a loss of 3 dB, but we have no idea of the number of watts present at either end of the wire, only that there's a 3 dB difference between one end and the other. But watch what happens if we designate one of these two power variables as a reference. If we set P2 equal to 1 milliwatt, for example, and this is very important, we then have to designate this new form of the dB as something else. We're going to call it the dBm, where M stands for milliwatt. Now we've added a whole new tool to our toolbox. We can speak of a 3 dB gain or loss, which is relative, or we can use the dBm to indicate an absolute number of watts. So, A level of plus 4 dBm, which is 4 dB above 1 milliwatt, is equal to 2.51 milliwatts. 3 dB is an expression of a ratio, and it's blind to actual amounts involved. But 3 dBm is an actual measurement of a quantity of power expressed in milliwatts. Well, what happens if you don't care about power? What if I'm interested in voltage, which is much more common in audio these days? Power is cheap. We care about signal levels, which are measured in volts. Well, can the decibel be used to describe voltage ratios, or even absolute levels? Well, you might be tempted to say no, and in a sense, you'd be right. Because, hey, power does not equal voltage, and you can't simply change the rules and substitute volts for power. But maybe there is a way. To understand this next part, we will have to go into Ohm's law, which describes the relationship between power in watts and electromotive force in volts. Ohm's law states that P, power in watts, equals E squared divided by R. So we could legitimately say that the decibel is equal to 10 times the log of E squared over R divided by E squared over R. Now, since voltage is most often measured in open circuit conditions, we can make the R go away. This conveniently reduces down to dB equals 10 times the log of E squared divided by E squared. One of the rules of manipulating logs lets us move that square from the fraction out here in front. So we end up with 2 times 10 times log of E over E. So if we change the multiplier from 10 to 20, 2 times 10, we can now use the decibel to express a ratio of voltages such as we do in signal to noise. If we choose a reference for one of the variables, just like we did with the dBm, and let's say this time we choose 1 volt, we can now have this new tool, which we call the dBV, and use it to measure actual quantities. In Pro Audio, the reference that's preferred is 0.775 volts, and that unit is called the dBu. Alright, we now come to the last part of the video, the use of the decibel to quantify sound. And here is where the decibel really shines. Acoustic power can certainly be expressed in dB, and often is. But what's generally more interesting to us and far easier to measure is sound pressure. Our ears in general interpret an increase in sound pressure as an increase in loudness. Pressure is measured in pascals. An amazing fact about our ears is that the softest sound we can perceive corresponds to a pressure of 20 micropascals, or 0.00002 pascals. The loudest sound we can tolerate before we experience pain is somewhere around 200 pascals. Well, that's a range of 10 million to 1. These are big numbers. We need the decibel desperately. Pressure in pascals is a field quantity, very much like voltage as it turns out. So if we use the 20 multiplier for the log of the ratio, we can use the dB to quantify changes in sound pressure level. If we use the threshold of hearing of 20 micropascals as a reference and call this new unit the dBSPL, we now have a way to express actual sound pressures without having to use pascals or deal with huge numbers. So let's recap. The decibel always expresses a ratio between two numbers. The dB without a suffix expresses the difference between two powers, or with a little math magic, the difference between two voltages or even sound pressure levels. When we add suffixes to the dB, like dBm, dBu, dBV, dBSPL, we're using the dB to indicate absolute values relative to some known reference. One final thought. Let's be consistent and let's be accurate when we use the dB. If we're talking about a simple change, dB without a suffix is sufficient. Turn that down by 3 dB. Can you give me about 10 dB more? Right? If we're talking about absolute levels, like, hey, please don't let the sound pressure level exceed 98 dB, we must add SPL if we're going to be accurate, okay? So turn it down 3 dB, that's fine. Don't let the sound pressure exceed 98 dB SPL. Okay, until next time, I'm Doug Jones.